Hello, and thank you for joining today's Environment and Energy Leader webinar titled A Case Study of PFAS in Wastewater Influent and Effluent, sponsored by Enthalpy Analytical, a subsidiary of Montrose Environmental Group. My name is Jessica Hunt, and I'm the Director of Live Events for E&E Leader. We appreciate everyone joining us live, and a large thank you in advance to those who will be watching this on demand. Before I hand the presentation over to today's speaker, I want to go over a few housekeeping items. If you experience technical difficulties during the event, please follow the troubleshooting tips located in the Help widget at the bottom of your console. If you are still having issues following the steps, please send a message to me via the Q&A widget, which is open on the top right part of your screen. Please feel free to submit questions at any point during today's event. All questions received will be forwarded to the team at Montrose Environmental. This includes questions submitted during on-demand viewing. At this point, I'm going to hand the presentation over to Lindsay Boone, Program Manager at Enthalpy Analytical. Lindsay, thank you in advance for sharing your expertise and time with us this afternoon.
Hi. My name is Lindsay Boone. I'm the Technical Program Manager with Enthalpy Analytical's UltraTrace Laboratory, located in Wilmington, North Carolina. And today I'm going to be presenting a case study of PFAS in wastewater, influent, and effluent. So to start off, I'd like to go over with what PFAS is. So PFAS isn't one compound, it's a class of compounds. There are over 4,500 of these things out there. PFAS stands for Per and Polyfluorinated Alkyl Substances. And in chemistry, there's a lot to be said by the name of a compound. So I always like to start by going over what exactly per and polyfluorinated alkyl substances mean. So if you look down at the screen, I've got examples of perfluorinated compounds under PFOA and PFAS, and a polyfluorinated compound under 6,2-FTS. Now, if we go back to this alkyl part of the name, what the alkyl is talking about in chemistry are all the carbon atoms with the C's and the points in these molecules. Those are all carbon atoms. They're talking about the carbon atoms in the molecule's backbone. So the backbone of perfluorinated and polyfluorinated atoms are carbons. And that's important because a lot of times PFAS compounds get referred to by how many carbons are in that backbone. So you can have C8s, C6s, or C4s. A lot of legacy PFAS that have been around for a while will be referred to as C8s. Now, per and polyfluorinated. Perfluorinated, again, is under here for PFOA, PFAS, and that's talking about all these carbon-fluorine bonds. Same for polyfluorinated. The main difference is, in a polyfluorinated compound, not all of the bonds to carbon are for fluorine. You still have some other bonds, like the carbon-carbon bond here. Now, that's important in sample matrices that are complex, like wastewater influent and effluent, even landfill leachate, because in the presence of oxidative chemicals and high heat, those polyfluorinated compounds can degrade into shorter PFAS compounds. So PFOA and PFAS are the most widely studied of all of these compounds, and again are legacy PFAS. PFOA was manufactured by DuPont and used in Teflon, and PFAS was manufactured by 3M and used in AFFF firefighting foam. Now, if you think about the two uses of those compounds, they had to have strong molecules that could hold up to high heat, and that's where that carbon-fluorine bond comes into play. Carbon is a positive atom on the periodic table, and fluorine is the most electronegative. So you've got a positive and a negative coming together. That's a super strong bond that can hold up to high heat, and that's why, again, these things can be referred to as forever chemicals. Once the bond is formed, it's really hard to break, and they can be hard to biodegrade, and they can bioaccumulate in the environment. So PFOA and PFAS, we know they have adverse health effects to humans, so we can't manufacture those in the United States anymore. So the 6,2-FTS, side note, that is commonly used as a replacement product in firefighting foam now. So because you can't manufacture PFOA and PFAS in the United States anymore, what the industries start doing is making replacement compounds. So replacement compounds usually have the same or similar chemical properties to those legacy PFAS. A lot of times they're just shorter in chain length. They get referred to as C4s and C6s commonly. problem with the replacement compounds is a lot of time the precursors used in the industrial processes or synthetic routes, like this one at the bottom of the screen, 6,2-fluorotellumer correlate, are used in the manufacturing process to make the shorter PFAS compounds. Some examples of replacement compounds that I see common in wastewater are PFBA and PFBS. PFBA is a compound that's used in food packaging and film. So if you think about your hamburger wrappers or the inside of those pizza boxes, that shine or sheen on there can be a compound like PFBA. PFBS is commonly used in surfactants, repellents, metal plating, pesticides, and flame retardants. So if you're a wastewater treatment plant with a metal plating facility on your industrial waste permit, you might have PFBS. PFBS is another compound that I'll see common in rural areas of the state, of different states, because of its use in agricultural processes like pesticides. So just because you're in a rural community and you've got a drinking water well that you don't think would be impacted by an industry, you could still be impacted by PFAS because of a compound like PFBS. Common uses of PFAS, AFFF firefighting foam we talked about. Now, firefighting foam gets a lot of attention because it was used in really high concentrations in the manufacturing process of the specific firefighting foam AFFF. So now the EPA has a health advisory associated with PFOA and PFAS, for example, at 70 part per trillion. And if these compounds, or PFOS in particular, was used in the manufacturing process of AFFF, you can see that at the part per million range. So where there was a lot of industry and a lot of firefighting training activity going on, you could really saturate an area. Household products like Teflon we spoke about. And then PFAS are used in a lot of different consumer products. One of the highest hits that I've seen in our laboratory was actually in a woman's eye makeup, and it was a 6,000 part per trillion hit for PFOS. So just because we can't make PFOS in the United States anymore doesn't mean that other industries aren't producing these products and they're winding up in our landfills and then again in our waste streams, and they can impact wastewater. Other common consumer products I've seen PFAS in have been sunscreens as well as lotion. So if you think about it, anything with a potential SPF factor could have PFAS in it. Now, not all of these products have PFAS in it, but I've seen several that do. Food wrappers is another one we spoke about. Stain resistant and waterproof. So PFAS was used in Scotchgard. So the Tennessee Valley area of our country, where there's a lot of carpet manufacturing, has been greatly impacted by PFAS, especially for wastewater treatment plants that took that waste from those carpet manufacturers and land applied their biosolids. So health concerns. So this is Roger Bellot. He was the lawyer that brought about the big lawsuit in Parkersburg, West Virginia against DuPont. One interesting thing that came out of that lawsuit was one of the largest human toxicology study ever done in the United States. You had a small town with multi-generational exposure to PFAS. And I think the lawsuit offered, maybe $300 a pop to give their blood. So you had moms bringing in the kids, the grandparents. It was such a large data set. It took the scientists and doctors 7 years to go over all the data, and at the end of that, they did find there are certain adverse health effects associated to the PFOA and PFAS compounds, and that's why those two were not allowed to manufacture in the United States anymore. So where are PFAS? So this isn't necessarily a map of where they are. It's a map of where the testing has occurred. So for the particular case study I'm going to be talking about today, we're going to focus on North Carolina and the North Carolina Cape Fear River Basin. So if you look at the map, that blue outline right there is a pretty good outline of our Cape Fear River Basin, and a lot of testing has occurred there because there's a manufacturing facility of a specific PFAS compound. Over here in Tennessee, Alabama, Georgia, you've got the carpet manufacturers, and you've got a major industry that produces PFAS in Alabama. Out in California, they're already testing landfills, metal plating facilities, and I know wastewater treatment plants started testing frequently in October of last year, as well as airports. So getting into our particular study. So the North Carolina Department of Environmental Quality asked about 20 wastewater treatment plants in the Cape Fear River Basin to test their influent for PFAS. specifically 21 PFAS compounds over, again, a 3-month period. And they wanted the influent to be grab sampling, and they wanted the lab to be DoD or Department of Defense accredited and use the DoD Table B15 isotope dilution method for the analysis. Now again, the reason why the North Carolina Department of Environmental Quality, or DEQ, focused on the Cape Fear River Basin is because in 2009, DuPont, which is now Chemours, started manufacturing a replacement product for PFOA at their facility in Fayetteville, North Carolina. That compound was Gen X. So Gen X has greatly impacted the Cape Fear River Basin. Chemours was putting waste into the Cape Fear, so therefore it was impacting the wastewater treatment plants and the drinking water facilities downstream, but they were also burning it off, so it was impacting private wells and lakes upstream of the facility as well. So just to point out the study, the reason why the DEQ focused on the region of North Carolina is because of the concentration of PFAS in that area. So I mentioned that the North Carolina DEQ asked these wastewater treatment plants to specifically use the Department of Defense Table B15 method. So I just want to briefly go over different analytical method options that are available for PFAS testing. So in the realm of PFAS, analytical methods are extremely matrix dependent. The EPA has 2 methods out for drinking water that are specific for drinking water. The first method that came out was 537. Now it's updated to 537.1. That's a drinking water method, and it can be required to demonstrate compliance. You get 18 compounds with that. Only a few states accredit for it. Where we sit in North Carolina does not actually accredit for PFAS. We hold our primary accreditation through the state of Florida. However, because this method could only be used for drinking water, it was not appropriate for the wastewater study. EPA 533 is a newer drinking water method that came out. It utilizes an analytical technique called isotope dilution. I won't go into the details of isotope dilution, but it's really the gold standard in analytical techniques for PFAS. And with that method, you get 25 compounds reported. 533 came about because 537.1 wasn't doing a great job on the shorter chain PFAS compounds or those replacement compounds I mentioned earlier, like the C4s. EPA 8327 is a relatively new method that came out. It was not available at the time the study was occurring. It's a direct inject method for the solid waste industry. It's got higher reporting limits, and it's not that specific. It's more of, are the PFAS there or are they not? Now, EPA 1633 is not out yet, but it is also going to be utilizing isotope dilution. Right now, EPA 1633 is in a multi-lab validation study, and so we don't expect it to be published and ready to use until 2023. This is going to be a great method for non-potable matrices. So if this method was available at the time of this study, it might have been the go-to method. It's going to report 40 PFAS compounds, and it was kind of a collaborative effort between the Department of Defense and the EPA. So finally, the analytical method that North Carolina DEQ wanted was PFAS by isotope dilution. Now, PFAS by isotope dilution can be referred to by a number of different acronyms. A lot of times people will refer to this, or labs will refer to it as modified 537 or 537.1, PFAS by LC-MS-MS, that's just the instrument it's ran on, PFAS by Table B15, or PFAS by DoD QSM Table B15. Now, to actually run it per Department of Defense QSM Table B15, a lab has to be DoD accredited. And there are a lot of extra parameters that a lab has to undertake to run this method, including tighter recovery criteria. And if any recovery criteria fail, you have to run the samples in duplicate. And because wastewater is a complex sample matrix, a lot of the recoveries would fail for certain compounds. And so we did have to run a lot of these in duplicate. Now, North Carolina only wanted 21 PFAS reported, but I do want to point out that this DoD QSM Table B15 allows us to increase the number of PFAS that are reported, and we can use it on a wide variety of sample matrices, from drinking water to effluent to biosolids to leachate to even that makeup I was speaking about earlier. So wastewater influent, as we know, is a very complex sample matrix. We started seeing a high amount of particulate in the sample matrices of the wastewater influent, and so one question as a lab that came up was, do the amount of particulate present in a wastewater sample like influence the PFAS, the representative PFAS present in the sample? So say if I pull a duplicate, and you're never going to pull a true duplicate in a non-homogeneous sample, is there going to be a lot of variability if I'm running these things in duplicate or triplicate? So what we wanted to see first was, do these PFAS partition between the aqueous layer and the particulate layer of the sample? So the way we did this was we actually separated the particulate from the aqueous portion of the sample. We centrifuged the sample to form a pellet, decanted off the aqueous portion, and did separate extractions on the pellet and on the aqueous portion. So we're almost treating it as two different samples. Now, our theory was that the longer PFAS, like the C8s or C9s, like PFAS here, that have a longer hydrophobic tail, all those carbon-fluorine bonds are hydrophobic, would be less likely to be water soluble, so they might be tied up in the particulate. And the shorter PFAS compounds, like PFBA, would be more water soluble and be in that aqueous portion of the sample. So these were true samples, so we weren't actually spiking them. You know, it was just kind of what PFAS were present in a high enough concentration to get some statistical data out of them. And on this side of the screen, you can see the compounds that were present in the sample. And in parentheses, that's the chain length. So we would expect the PFNA, which is a C9, to be less water soluble than the PFHXA, or C6. So again, we were thinking that the less soluble compounds might stick to the solids, and these were our expected outcomes. We also wanted to look at overall reproducibility. So we analyzed the sample as a whole in triplicate to look at the overall reproducibility. If you're trying to find duplicates or doing splits between laboratories, how that would work out in a complex sample matrix like wastewater. And what we saw for each of these analytes, what this table represents, is the percent RSD for 3 replicates. And most of the PFAS were under 10%, which is really good, you know, when taking into account the analytical methodology as well as the complex sample matrix. But what about the particulate? Did certain PFAS stick to the particulate? So what this graph shows is the average partitioning behavior in a sample. So on your x-axis, you have the PFAS compounds that were present, and on the y-axis is the percent of the whole sample contents. The blue bar is the percent of the sample that was present in the aqueous portion, and the orange bar was the percent that was present in the pellet. And as you can see, it pretty much was all in the blue bars. So these things were they're very water soluble. So the amount of particulate didn't really play a big part in partitioning PFAS throughout that sample. We did get a little PFAS, which is a C8, in the pellet. So that's good for us as a laboratory because we really have to work extra hard to make sure we sonicate that particulate to extract any PFAS. And most of it in this particular instance was already present in the aqueous portion of the sample. So you're more likely to get better reproducibility when running duplicates or triplicate analyses. Now, a side note that we came across when we were looking at this study was the ionization suppression. So what is ionization suppression? Essentially, it's anything in the sample that causes an instrument signal to be reduced. So this is really important for PFAS because you're looking and trying to analyze things at a tiny level, part per trillion, which is like a grain of sand in a Olympic-sized swimming pool. So ionization suppression can be thought of as any interference that's co-extracted with a PFAS that can cause a signal to be reduced again. So our original thought was a more complex or dirty sample matrices would have an increased level of ionization suppression compared to a clean homogeneous matrix like drinking water. So does that particulate matter contribute? So what this graph shows is on the x-axis, the sample portion, y-axis, the recovery of the injection standard. So the QC samples here represent a clean sample, almost a perfect sample with no ionization suppression. So what we do with these QC or quality control samples is we spike in isotopically labeled analytes, PFOA and PFAS, right before the sample goes on our instrument for analysis. So these should have a perfect recovery, no ionization suppression. And then we looked at the ionization suppression in the whole sample. So that's the aqueous and the particulate layers combined, just the aqueous, and then the solids. And so if you think about it, a perfect sample would be the same height as this quality control sample. And as you can see, the solid actually has less ionization suppression, or it's more in tune with that QC sample than both the combined sample as well as the aqueous portion alone. So what that tells us, any compounds that are causing ionization suppression are getting co-extracted in the aqueous portion of the sample with the PFAS. So it's not necessarily true to say that a more complex sample matrix like wastewater will cause ionization suppression. So for the partitioning portion of this study, the conclusion is not what we originally thought. In this study, the PFAS that we measured don't significantly absorb on the particulate matter. So that's only the PFAS that we were able to measure in this study. And the ionization suppressing compounds don't absorb on the particulate matter either. They're more in that aqueous or the whole sample because they're pretty water soluble. And the overall variability of particulate in an influent sample shouldn't greatly affect the results when running duplicates due to partitioning behavior. So the next portion of our wastewater study that we did was looking at TOPS analysis using influent and effluent. So TOPS stands for total oxidizable precursor assay. So when we were working with a lot of these plants on running that 3 months worth of samples, what we saw a common occurrence was degradation products. So as I mentioned earlier, when you have a polyfluorinated compound, the example I have here is 6,2-FTS. You can break the bond between the carbon-carbon bonds. The carbon fluorines are pretty stable, but the carbon-carbon bond would break. So this can be done with heat and in the presence of oxidative chemicals. And a lot of these plants were also running effluent at the same time as their influent. So what we saw that sparked this study was 6,2-FTS would be high in an influent, around 1,800 part per trillion. But then we pulled the corresponding effluent, it would have significantly decreased, as the table on the screen shows. And then smaller or shorter chain PFAS compounds like PFHXA would have increased from influent to effluent. And just a side note, PFHXA is a terminal PFAS compound. It's not going to degrade anymore. It's a happy molecule. It's in its lowest energy state. So in this particular instant, the PFHXA increased by 50 part per trillion. So water resource managers, consultants, chemists, and engineers are really trying to figure out, well, where's it all going? The math doesn't add up or make sense. So one analytical tool that we have in our toolbox is the TOPS or TOPA analysis, total oxidizable precursor assay. So this is kind of a maximum or worst case estimate of PFAS composition in your sample. It's only going to be really applicable to more complex sample matrices like your wastewater, and whenever you have higher amounts, like in the part per billion. So what we do with the TOPS analysis as a lab is we take your sample and we analyze it using isotope dilution, just as we normally would, and report all the individual PFAS concentrations. So say those 21 compounds from the DEQ study will get reported. But we also take a portion of that sample and we oxidize it. So we treat it with heat and oxidative chemicals. So what that does is in a complex sample, any known or unknown precursors that are present in that sample that could turn into a PFAS are forced to do so. So if you look at the difference between the unoxidized and oxidized portion of your sample, you can kind of get a worst case estimate of what could go on between, say, a wastewater treatment plant, influent, and effluent. So what we did in this particular study was we collected influent and effluent samples where we wanted to compare the magnitude of the PFAS precursors. Samples were taken from the same wastewater treatment plant at the same time points. We allowed for a 24-hour lag time between influent and effluent because there was about a 24-hour lag time, like for example, if you're trying to follow that same drop of water through the treatment process. So we collected the effluent 24 hours after we collected the influent. So what this chart shows on the x-axis is you have all the measurable PFAS compounds that were present in an influent, both in the unoxidized and oxidized sample. The y-axis is your concentration in nanogram per liter. So the pre-oxidized sample, as is in green. So you can see 6,2 FTS was around 16,000 part per trillion before oxidation. After oxidation, it decreased to 0, which makes sense because I forced everything to those shorter chain PFAS that we can measure. So the fact that this went to 0 also as a chemist lets me know that my reaction has gotten to completion. And what you can see happening is the longer chain PFAS decrease and the shorter chain PFAS increase. The chain length is in parentheses. So for instance, PFBA wasn't present pre-oxidized, but it was present post-oxidized. And another side note that we saw was that most of these were degrading into the corresponding carboxylic acids, not the sulfonic acid groups. So overall, in this particular influent sample, there was about a 6,239 part per trillion difference between pre-oxidized and post-oxidized samples. So that was about 6,000 part per trillion of PFAS, unknown precursors that we weren't measuring if we did not do the TOPS analysis. Now we did the exact same thing for an effluent. And again, you can see 6,2 FTS was around 5,500 part per trillion in our pre-oxidized sample, and it went to 0 in the post-oxidized. And the same thing. You had the shorter chain PFAS increasing. Now, this was from the same wastewater treatment plant, and as you can see, the bars look different between influent and effluent. So what that tells me is there's a different fingerprint of PFAS present in the influent and the effluent. So something's going on in that water, in the treatment process that's changing the types of PFAS that we're seeing between influent and effluent. And that effluent sample, there was about a 4,800 part per trillion difference between your post-oxidized and pre-oxidized sample. Now, the major and overall conclusion, and that again interests us, was the difference in fingerprinting patterns of the PFAS between the influent and effluent. What this chart shows is influent and effluent. Influent is the blue bars, effluent is the orange bars after oxidation. And here's the concentration on the y-axis. Now, if the fingerprinting pattern was similar, those bars would be the same between influent and effluent. However, you can tell they're not. So something's going on in the treatment process that's causing the PFAS to change. Where is it going? Is it going to the dewatering ponds? Is it going to the biosolids? Those are things that we're interested in trying to find out. Another analysis that we could utilize in the future would be total organic fluorine. Looking at the difference between the numbers we get between the TOPS analysis and total organic fluorine might be interesting. Total organic fluorine uses an instrument called a combustion ion chromatography system. The idea is there's not a lot of naturally occurring organic fluorine, so if it's there, it's probably from a PFAS compound. So what the lab does is they measure the free fluorine in your sample, and then we combust it and measure the total fluorine. The difference is total organic fluorine. This has high reporting limits, so again, you probably need to have ppb levels of PFAS for this to make sense as an analysis. Just a couple of things I always want to mention when I do this presentation, and I know we've got some extra time, is thinking about sampling procedures. I spoke about how PFAS is it can be present in a lot of consumer products. So the worst thing as a drinking water or a wastewater plant you want to do is contaminate your sample. So you really have to think about the clothing that you're wearing. The recommendation is 100% cotton clothing. Avoid Gore-Tex or dry fit clothing. Those things can have PFAS. Avoid certain products, like I mentioned, your sunscreens, your makeups, your lotions. You want to make sure you always use the containers that the lab provides you. We like to send out polypropylene containers that we know are PFAS free, because this is in Teflon again, and a lot of sampling jars can be Teflon. Make sure your sampling material and the equipment you use are appropriate. We like to use stainless steel dippers for these grab samples. There are PFAS-free hand balers if you need to use them for a well. And also, if you have to use a pump, make sure you're not using Teflon tubing. Just make sure you take extra precautions whenever you're testing for PFAS as to not contaminate your sample. And always work with the lab to make sure you're filling out your chain of custody correctly, because there are, for our lab, for instance, we can test for over 70 of these, and there's all the different types of methods. So you want to make sure that you're choosing the right method to get you the answers that make sense for the study that you're planning. And I just wanted to end by mentioning UCMR5. UCMR5 is going to be a combination EPA 537.1 method as well as EPA 533. I mentioned before that EPA 533 can test for 25 compounds. UCMR5 is going to report all 25 compounds from EPA 533. And it's also going to report the 4 compounds that don't overlap from 537.1. So just make sure, if you're a drinking water facility out there, or even a wastewater facility, that you're looking for those 29 compounds from UCMR5 when you're planning your sampling events, even today, so you can kind of get an idea where you're going to stand when that when that rule comes out. So with that, I'm going to conclude this presentation. Thank you all for listening. Here is my contact information. If you have any questions, feel free to send me an email or reach out to me directly via my cell phone number. I'm always available to talk about PFAS and to try to answer any questions that you have on analytical methods, as well as sampling techniques, and so on and so forth.